Okay. Hi everyone. Myself Vinit. Today I will teach an important topic, important portion of thermodynamics, that is entropy. First of all, I will teach you what is entropy, then moving towards entropy change, then how can we find entropy change for reversible process in case of ideal gas, then we will move forward for entropy change for reversible phase transformation, then we will find entropy change for irreversible phase transformation. Okay, so yeah. First, I will teach you what is entropy. Entropy usually tells you about randomness in a system. Randomness of what? Randomness of molecules in a system. Okay. Or disorderness. For example, we have solid state, liquid state, as well as gaseous state. In gaseous state, molecules are not closely packed as we compare in solid state. So they are free to move anywhere. On the other side, we have solid state. Usually molecules are bound. They are bound to a system and they are not free to move anywhere. Okay. So usually entropy tells you about randomness or disorderness. Okay. We have solid state. We have liquid state. We have gaseous state. Okay. So here in the system, molecules are closely packed. Okay. But in gaseous state, molecules are not closely packed. Okay. So they are free to move here, 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 anywhere where they find space. Okay. Why I am teaching this? Because there is a question which was asked in Jan 2016 on the basis of this particular portion. What was the question? The question was correct order of entropy for CO2 gas, CO2 liquid, CO2 solid. The answer is simple. The randomness in gaseous state is much more as compared with the solid state. So answer is this. This is the correct answer. Okay. Now I am moving towards what is entropy change. Okay. So entropy change tells you about heat change reversibly at a particular temperature. That means the amount of heat, this amount of heat required by the system to not increase the temperature, but to change the intermolecular interaction between the molecules. That particular amount of heat at particular temperature is known as entropy change. This equation is very important, very important, because this equation will be used to calculate entropy change for reversible process, for reversible phase transformation, and for irreversible phase transformation. Okay. Now we have to calculate, first of all, entropy change we have to calculate for reversible process. In ideal gas, remember this, we will find entropy change for ideal gas only. Then we will move forward towards reversible phase transformation, then towards irreversible phase transformation. Okay. So first process is reversible phase transformation in case of idle gas. Okay. So for reversible process, like we have H2O solid, okay, converting into H2O liquid. Okay. So this is a process in which solid state is converting into liquid state at like 0 degrees Celsius, and at assume it temperature T1 and temperature T2, pressure P1 and pressure P2. Okay. So how can we calculate entropy change for reversible process? Okay. We can calculate entropy change by using the equation we actually talk about, that is heat change reversibly at a particular temperature T. Okay. From first law of thermodynamics, internal energy change is equal to heat change plus work done, and work done is equal to minus PdV. So heat change is equal to internal energy plus PdV. Okay. And as we are talking about idle gas, so internal energy change is equal to NCV dt for idle gas. Okay. Put this whole form into this particular equation, we get entropy change is equal to NCV dt plus PdV at particular temperature T. Okay. And we know that for ideal gas, PV is equal to RT. So we can write P is equal to RT upon V. Okay. Put this system into this, entropy change is equal to NCV dt by T plus R dV by V. Okay. Integrate this corresponding to temperature T1 to T2 from volume V1 to V2. We will get entropy change is equal to NCV ln T2 by T1 plus nR ln V2 by V1. So this is the entropy change for reversible process when we have different variables like T1, T2, V1, V2. Okay. So here in this equation, variables are different. This is one of the most important points in entropy. Okay. As we know that in this equation we relate temperature and volume. In a similar fashion, we can relate temperature and pressure. How? Okay. So relation between temperature and pressure for entropy change. Since we know that entropy change is equal to heat change reversibly at a particular temperature T, which is equal to mCV dt plus PdV divided by T. Okay. As we know that PV is equal to RT, as we are talking about ideal gas, on differentiating this, we get PdV plus VdP, which is equal to TdR plus RdT. Since R is a universal gas constant, so change in universal gas constant comes out to be 0. Okay. So what we have, we can write PdV is equal to RdT minus VdP. Okay. Put this PdV in that particular equation, we get is equal to NCV plus R into dt divided by T minus VdP divided by T. Okay. By placing PV is equal to RT. So from V by T is equal to R by P. Put V by T is equal to R by P and integrate corresponding to from T1 to T2 and from P1 to P2. We get entropy change is equal to NCP ln T2 by T1 plus NR ln P1 by P2. Okay. How Cp comes here? Because we are using Cv plus R, which is equal to Cp. Okay. So result comes out to be for reversible phase for reversible process. For reversible process, while we are calculating entropy change, variables must be different. This is a must situation. Variables, that means temperature, which is moving towards T2, T1 moving towards P2, V1 is changing to V2. So this must happen for reversible process while we are calculating entropy change. Okay. Now we have to calculate entropy change for reversible phase transformation. How can we calculate entropy change for reversible phase transformation? First of all, we have to know about what is reversible phase transformation. What is phase transformation? We can describe it by using a simple example of converting H2O solid into H2O liquid. Okay. So in reversible process, same thing happens. Okay. Wait a second. In reversible process, same thing happens. Like H2O solid converts into H2O liquid. But here these variables are changing. That is from T1 is moving towards T2 and T1 is changing towards P2. Okay. But in this process, in reversible phase transformation, during the transformation of one phase to other, pressure as well as temperature remain same. There will be no change in these kind of variables. If these changes, then it will not be a reversible phase transformation. Either it will move towards irreversible phase transformation or it will move towards reversible process. Okay. And we know that while we are converting solid phase of water into liquid phase of water, temperature remains constant at 0 degrees Celsius and 1 atmosphere pressure. Okay. Okay. We will use same repeating formula, that is entropy change is equal to heat exchange reversibly at particular temperature. Same particular formula. We will use this in irreversible phase transformation as well. But after which there is a change and it will give different formula. How? Since we know that enthalpy is a summation of internal energy and PV. Okay. Change in enthalpy gives you change in internal energy and change in PV. This will result into enthalpy change in internal energy plus PdV plus VdP. Okay. Since we know that reversible phase transformation occur at constant pressure, so this dP comes out to be 0. Okay. So dH is equal to this, and this whole is equal to change in energy, that is heat exchange for first law of thermodynamics. Okay, then we will put dq is equal to th, that is change in enthalpy at particular temperature. So entropy change for reversible phase transformation comes out to be enthalpy change divided by temperature. Okay. Let us assume a question for this. Okay. Calculate entropy change for this process, that is H2O liquid convert into H2 vapors. Okay, we can assume reversible phase transformation by seeing this reversible, that is reversible sign, that is this. Okay, and by seeing there is no change in temperature and pressure. Okay, for example, this will occur at 100 degrees Celsius and 1 atmosphere pressure. Okay, and you are giving that enthalpy of vaporization is equal to x kilojoule per mole. Okay, so we can easily find entropy change for reversible phase transformation. As we know, enthalpy of vaporization divided by temperature. Since vaporization occur at boiling point, so we'll put boiling point here. Okay, and it was given that x kilojoule per mole. Okay, and boiling point for water, if it is not mentioned in the question, we can think we know that at 100 degrees Celsius water boils. Okay, so we will put 373 Kelvin. Okay, so we will get x by 373 kilojoule per Kelvin per mole. So this is the required answer we have. Okay, now I am moving towards another important topic, which is very important, and usually most of the question in entropy change is asked and will be asked in the future from this particular topic, and that is irreversible phase transformation. Okay, why this topic is important? Because it includes reversible phase transformation as well. Okay, so for while solving irreversible problem, we have to use reversible phase transformation knowledge as well. That is why this topic is one of the important for entropy calculation, entropy change calculation. Okay, so how can we find entropy change for irreversible phase transformation? Okay, so for example, we have example of like H2O solid, which is converting into H2O liquid at this its temperature is 0 degrees Celsius, but its temperature is 25 degrees Celsius at 1 atmosphere pressure. Okay, okay. So since you know that this example is not from the reversible phase transformation, because variable is changing. Okay, that is from 0 degrees Celsius to 25 degrees Celsius. Okay, and also not from reversible phase as well. So how can we calculate this irreversible phase transformation? The answer is simple, that is by converting this irreversible phase transformation into reversible phase. How can we do? we know that H2O solid usually convert into H2O liquid at 0 degrees Celsius. This phase is in equilibrium with this phase at 0 degrees Celsius and 1 atmosphere pressure. Okay. Now we are given that H2O liquid at 25 degrees Celsius at 1 atmosphere pressure. Okay. So as it was given in the question that H2O solid at 0 degrees Celsius and 1 atmosphere is converting into this H2O liquid at 25 degrees Celsius and 1 atmosphere pressure, it must have to pass through this particular rectangular box, this particular phase. It must have to pass through it. Okay. And now it is very simple. We can calculate entropy change for reversible phase transformation by using this formula, that is enthalpy change of fusion at melting point. Okay, and this we know that entropy change is equal to these pressure is changing as well as temperature is changing. So entropy change can be given as NCV ln T2 by T1 plus nr ln V2 by V1. Okay, and whole entropy comes out to be, total entropy comes out to be this first part and entropy change for second part. This is the way we can find the entropy change. Okay. Now this can be further I can show you an example by which this irreversible phase transformation will be more clear. Okay. So this is the question which was asked in GATE exam, previous year GATE exam question, and we know that GATE exam question are more important because previous year GATE exam question will be asked in the nearby future JAM exam. That is why GATE exam question is important. And how can we so the question which was asked in GATE exam, that is conversion of H2O liquid, H2O vapors at 373 Kelvin, and this phase is present at 1 atmosphere and this phase is present at 0.1 atmosphere. And in GATE they asked that calculate entropy change for whole process. As we know that liquid phase is converting into vapor phase, temperature is same but pressure is different. So this is not an example of reversible phase transformation. So we will move forward towards irreversible phase transformation. As we know that irreversible phase transformation can be solved by converting it into a number of reversible phase transformation. So we will convert H2O liquid into H2O vapor first. This will occur at 373 Kelvin and 373 Kelvin at 1 atmosphere. Okay, this will convert into H2O vapor. Now this pressure can be changed. Okay, so we know that this is the reversible phase and this is irreversible phase. This is the reversible phase transformation and this is the reversible process only. Here variables are changing. Here variables are not changing. Okay, so we will calculate the entropy change for the first process by using the formula, that is enthalpy change of vaporization divided at a particular temperature, and entropy change for this process can be calculated by using NCV ln T2 by T1 plus nr ln P1 by P2. Since we are using pressure, so we will convert CV into Cp. Okay. Now for first process, entropy change is equal to enthalpy of vaporization, and it was given that enthalpy of vaporization 40670 joule and temperature was 373 Kelvin, so it will be near about 109 joule per Kelvin. Okay, and entropy change for second process will be at constant pressure. It will be nR ln P1 by P2, which is 8.314 joule per Kelvin per mole ln of P1, that is 1 atmosphere, P2 0.1 atmosphere. It will be 19 joule per Kelvin, near about. So total entropy change for whole process comes out to be entropy change for first process and entropy change for second process. It will be near about 128 joule per Kelvin. So this is the required answer. Okay. So I did a silly mistake in the previous slide while teaching entropy change for reversible process. Yeah. Okay. For reversible process, usually the phase remains same. This was the mistake. Okay. I converted solid state into liquid state, but solid state will convert into solid state at different temperature and different pressure. Okay. So this was a mistake. Please remember this. Okay. So moving towards next slide, I will conclude all this, the reversible process, reversible phase transformation and irreversible phase transformation. In reversible process for ideal gas, remember, phase remains same. Solid will convert into solid or liquid will convert into liquid. Okay. And the temperature and pressure, they will deviate for sure. And for reversible phase transformation, phase changes, that is solid will convert into liquid, liquid will convert into vapors, and there is a sign this will be used for sure. And here temperature and pressure remain same. They will not deviate. So this is the major difference between a reversible process and for reversible phase transformation. Okay. So this is all about the entropy change calculation for all these three different processes. So this is all about the lecture. I hope you understand this entropy and entropy change and the calculation of entropy change for different process. So thank you very much.